Hi, I'm Minsara and today we'll look about quantum computing, what quantum parallelism is, and what superposition really buys you, alongside answering the question why a computer is not simply trying all answers at once. And I'll explain the answer to this question. What does it actually mean when people say quantum computers try every answer at once? It's the single most repeated line about this technology, and it's not quite right. Over the next few minutes, we are going to find out what superposition really buys you and why the truth is strange and more interesting than the myth. So, why we build these strange machines at all? Classical computers compute with transistors like tiny on-off switches, and for 60 years, making them smaller made everything faster. That shrinking is now bumping into the size of atoms themselves, and some problems simulating a molecules, breaking modern encryption, searching a vast space of possibilities grow fast that no amount of switch shrinking will ever catch. In 1981, the physicist Richard Feynman pointed out something radical. Nature itself runs on quantum rules, so simulating it on a classical machine will always be painfully slow. His proposal built a computer out of the same quantum matter it needs to simulate. A machine like that needs three ingredients: superposition, entanglement, and interference. That third one is where the real speed comes from, and it's what the rest of this video is about. This is the claim you heard: the quantum computer tries every answer at once. It sounds thrilling. A machine that checks a billion possibilities simultaneously and hands on you the winner. It's also the single biggest misconception in this field. So let's find out what's actually true, starting from the basics. A classical bit is like a light switch. It's forced to one of two positions, 0 or 1, nothing in between. A qubit is different. Picture a compass needle that can point anywhere on a sphere between those two poles. That in between isn't a trick, it's the actual object a quantum computer works with. So, here's the part almost every explainer gets wrong. Superposition isn't two coins existing at once. It's on state described by two numbers called amplitudes. One for 0, one for 1. That's how strongly each outcome is baked into that single state. That's the whole definition. No duplication, no parallel universe, just a receipt. Amplitudes behave like waves. Drop two stones in a pond and their ripples cross, sometimes piling it up into a taller wave, sometimes cancelling into a flat, still water. That single property, waves adding or cancelling, is the exact thing a quantum computer is built to exploit. And amplitudes can do something probabilities never can: point in a negative direction, which is what makes the cancelling possible in the first place. So, here's the catch the myth leaves out. However many amplitudes a qubit is holding, you only ever get one measurement. Reading a qubit collapses the entire superposition down to a single result chosen at random with odds set by those amplitudes. Every other possibility vanishes the instant you look. So if you only get one look, how does a quantum computer gain any advantage at all? This is the actual interference. A quantum algorithm choreographs its amplitudes so every path to a wrong answer cancels itself out, and every path to the right answer reinforces. You are not secretly reading all the answers. You are rigging the odds before you ever measure, which is the honest answer to our question. Quantum parallelism isn't a bigger search party checking more answers at once. It's a wave you learn to steer. Put side by side, the gap is clear. It's not that quantum computer sees every possibility. It's that it can only ever read out one. It's not faster at everything, only where a problem structure gives interference something to grab onto. Take search. Scanning an unsorted list classically takes roughly n tries. Grover's algorithm steers interference toward the answer in about the square root of n steps. A real provable speedup. Not instant, not magic, not genuinely faster. The same idea powers Shor's algorithm, which factors large number by exploiting their hidden periodic structure. The reason today's encryption has a long-term expiry date is why quantum computers can simulate molecules natively. Since modeling interaction electrons is itself a quantum problem, There's no universal faster at everything button, only problem with the right shape to interfere against. So superposition loads the dice. Interference rolls them. The qubit genuinely holds an exponential space of amplitudes. That part of the myth is real, but the speed comes from engineering how those amplitudes cancel and reinforce, one carefully designed algorithm at a time. That's what superposition really buys you.